they're not. The problem is there's no statewide mandates for masks or anything. It's all very local. Our city has one, but the county doesn't, and other cities don't. So it's all over the place, and this is part of the problem.
Okay.
But as far as I know, there's only one person I know personally who has actually been affected. That's one of my PhD students, who's actually affected very badly, unfortunately, for 3 weeks. Been down with COVID very badly. But mostly we're faring okay with all the restrictions.
Okay.
How are things there?
Here also nearly the same. Yeah. So here so many deaths are there all over India. But in Kerala, in our state, they are fighting very well. But still, once it is spread, there is no control.
Yeah, I know. In England, they're trying this tiered system, right? So each county has its own tier, and they were complaining that some of the very local places in those counties with low COVID rates are being lumped with their whole county that has high rates, and so the restrictions are actually worse now than they were before. And the minister was saying, oh, well, it doesn't respect boundaries. I'm thinking, well, if it doesn't respect boundaries, why are you separating into these tiers? It's the whole country. What? Each county is separated its own, and it doesn't make any sense to me, but they're doing better at controlling it than we are. So,
okay.
So I tried to work out how to share my screen a bit earlier, but there was no one on my call, so maybe that's why I couldn't do it. I can say present.
Okay, I can see the option below. There's a present now option is there.
Yeah, I see it now. It wasn't working when I tested it because I was the only one on my test call, I think. And let me see, why isn't this there's my window. So I want to present that. Doesn't, oh, there, is that it? Ah, there we go, okay. Let's see if that works. Okay, so you can see that?
Yes, we can see that. We can see.
Can you still hear me? Okay. Okay. All right. Shall I just make a start, or will someone introduce? Or
no. Actually, there is a formal introduction by our HOD, and then a research scholar will speak about you, and then we will start. Okay. So, Dr. CB.
Yes, sir. Hi, sir.
Please start.
Yes, sir. Today it is a very auspicious day because we have a very eminent professor with us. Rick Ubic is currently working as professor in Department of Material Science and Technology. And as you can see that he has an elaborate CV where he has published more than 150 articles in reputed international journals and more than 3,000 citations. So it is definitely our privilege. We are celebrating this 50 years of our existence in Department of Physics. I thank Professor to be with us for some time, and I also thank Dr. Subodh for arranging such a interaction session with the professor. So I hand over the session to Subodh to moderate and continue the proceedings. Dr. Subodh, please continue.
I would like to invite Ms. Adira Rajan, our research scholars, to formally introduce Professor Rick Ubic. Adira, please.
Yes, sir. Good morning, y'all. Department of Physics, University of Kerala is celebrating its Golden Jubilee. As part of our 50th anniversary celebrations, we have organized an invited talk by Professor Rick Ubic, Professor in the Micron School of Material Science and Engineering and Director of Boise State Center for Materials Characterization. His journey from a graduate to an eminent material scientist is an extremely motivating one. He obtained both his bachelor's and master's degree from the Department of Material Science and Engineering at Case Western Reserve University, USA. In 1998, he earned his PhD in engineering materials from the University of Sheffield, UK. He started his career as an assistant professor at Department of Materials, Queen Mary University of London in the year 1999 and was promoted to associate professor in 2005. He moved to Boise State University in the year 2007, where he is a professor now in the Micron School of Material Science and Engineering and served as the director of Boise State Center for Materials Characterization since 2012. Professor Ubic is a member of the Electron Microscopy and Analysis Group of the Institute of Physics. He also serves the American Ceramic Society as past chair of the Electronics Division and the member of the Publications Committee. He has been editor-in-chief of Material Research Bulletin since 2014. He was also a member of the Minerals, Metals and Materials Society, Association for Iron and Steel Technology, and ASM International. In 2014, he hosted the 8th International Conference on Micromaterials and Their Applications and remains as an active member of the International Advisory Board of this conference series. He has received several awards, including the American Ceramic Society's Robert L. Coble Award for Young Scholars for his contributions relating crystallography to the behavior of dielectric properties in complex compounds in the year 2004. In 2017, he became the recipient of Boise State's highest honor of research, the Foundation Scholar Award. His research work mainly involves structural characterizations of graphite and electroceramics, structural property relationship and correlative modeling of perovskites, including the effect of vacancies, ordering, and non-cubic distortions. He bagged about 150 scientific publications and a book entitled Micromaterials and Applications. He has more than 3,000 citations and acquired an H-index of 28. It is being a privilege to have Professor Rick Ubic on this occasion to deliver a talk on correlative models of some structural aspects of perovskites. With this brief introduction, we welcome you, sir.
Thank you, Akira. Well, that was possibly the most thorough introduction I've ever had. I'm quite humbled. And I'm very thankful to be invited. I'm very honored to be invited to speak to you on this occasion of your Golden Jubilee. So congratulations to everyone. I'll just make a start. So my talk I've titled Correlative Models of Some Structural Aspects of Perovskites. If anyone has a, can everyone hear me okay? I hope so. No one's answering.
Yes, sir.
All right, good. All right. So before I start giving a talk like this to such an international audience, I like to put our place in context geographically. So I'm sitting today, I don't know if you can see my mouse. Can anyone, I don't know if you can see my mouse. Maybe if I do this, there you go, maybe you can see that. This is Boise, Idaho. We sit here in the Pacific Northwest. No one has ever heard of Boise or much less visited us, I suppose. So Yellowstone National Park is here, about 586 kilometers away. Salt Lake City is down here. Portland is here, about 689, about 700 kilometers away. Seattle is here, 810. So we are here in the middle of all of that. We're in the mountain time zone in the Intermountain West, Pacific Northwest. So that's where we are. And we're about, I would say, half a mile, you might say 860 or so meters in elevation. That's where we are. Okay. So the other way I would start is with this sort of forewarning. George Box, the very famous statistician, wrote several times that all models are wrong, but some are useful. And I want you to keep that phrase in mind as I talk to you this morning. Realize I'm talking to you. Oh, is someone making a comment? Sorry. I realize as I'm talking to you that it's I'm not only talking to you tomorrow, because you're all in tomorrow as far as I can tell. I'm talking to you next month as well, so that's a bit strange for me. But I just want you to keep this phrase in mind. The other thing is our models that I'll show you, our correlative models, are very simple. I run them on an Excel spreadsheet. So the sentiment expressed here is that simple models, right, are far more elegant than the over-elaboration, over-parameterized, and there have been some of these in this field. So there you go. Let's move along. So why perovskites? I'll show you what perovskites are, because some of you may or may not be familiar with perovskites. It's a fairly simple archetypical material structure. The stoichiometry is AB, X, where A and B are cations, X is the anion, usually oxygen, for our purposes always oxygen, but not necessarily. Why we're studying them? They're everywhere, all right? Applications of perovskites are across the board in functional materials. And I just looked this up the other day. The number of publications that mention perovskites in their title or subjects has skyrocketed. It's about 5 times increase over the last 10 years. So there's a ton of research going on in perovskites generally, and they're going to be across the board here, right? One of the applications, which I guess most directly impacts what I'll present today, is heteroepitaxy. So the problem would be a lattice mismatch with silicon. Everyone wants to use silicon still. Gallium arsenide has a negative 3.5% lattice mismatch. Gallium nitride a positive 3.5% lattice mismatch. Indium phosphide is a whopping 20% mismatch. So it's difficult to grow them epitaxially. So how do you solve that problem? There are only a couple approaches. You can throw out silicon and use a different substrate. That's kind of a non-starter for most of electronics. So the other thing you can do is to use a buffer layer, something with a lattice constant between silicon and semiconductor you want to use, and that will help take up some of the strain without causing a lot of threading dislocations. If you want to do this, though, you need to know the lattice constant of the buffer you're using, or of the semiconductor you want to use, right? In order to know the lattice constant, you can do X-ray and refine it. You can do neutron diffraction. You can do an atomistic simulation before you actually make the material. All of those things can be time-consuming, difficult, and or expensive in terms of money or time or both, right? So it would be nice to have a simple way of doing this. This is a specific example from one of our master students several years ago. He was growing barium titanate, strontium titanate, two different perovskites together, a few atomic layers of one, a few atomic layers of the other, in these layered films like this. And the idea is that barium titanate is ferroelectric, has certain kind of electrical properties. Strontium has a different kind of electrical properties. And when you put them together, because they're different materials, barium is much bigger than strontium, you have different strains, and you can relieve some of the strain in the layers by alternating the materials like this in these stacks. And it also means you put some strain into the strontium and you make it ferroelectric as well. So there's all sorts of opportunities to engineer properties by varying the thicknesses and the frequency of these layers. They look like this. So that's one sort of superlattice engineering application of this sort of modeling work. And this diagram, I just like this diagram. It was published, gosh, over 10 years ago now. But it shows different substrate materials, perovskites, and the different perovskites you might want to put on them as films. And if you want to lattice match, this is a sort of a graphical way of showing how to lattice match. If you want a lattice match for this, you use something that's near here in the substrates. But if you want to be very precise, you need something more than just this gross sort of graphical representation. So that's where this work is more or less coming from. And that's about the year we started, actually. In 2007 was the date of our first paper in this field. Okay. So I said I'd introduce perovskites for those who weren't familiar. And this is your introduction, perovskite geometry. This is the archetypical cubic perovskite. Not many materials actually have this structure, but it's all the structures, perovskite structures are derived from this. So you have, there's your cations, A and B. So in this drawing, the gray atoms here are your A cations. The green guy in the middle there is your B cation. It's smaller and higher charged. And the blue things here are your anions. Like I said, for us, they're oxygens. And you see how they form this octahedron around the B. They're octahedrally coordinated around the B cation. That's the basic gist structurally of perovskite. That's one unit cell. If you put several together, you can see they're going to share corners, vertices of the octahedron, of the octahedra. And they're going to contain one B site in there. And if you connect up a lot of octahedra, they're inside the octahedra, you're going to have one A site that'll be 12 coordinated, cube octahedrally coordinated to the oxygens around it. And those are the ingredients for perovskite. In the cubic form, it's space group PM bar 3M. Okay. So if we want to describe the lattice constant of this cube, we have several ways of doing it. We first assume that anions and cations are in contact. And if that's the case, we can draw a face diagonal this way. And that's, remember, that's the A site. That's the X site. So we have two AX bond lengths, all right, or 2RA plus 2RX is equal to, just from Pythagoras, this is the square root of 2 times the lattice constant, right? That's the hypotenuse of this triangle. I hope you can follow my cursor there. Okay, so we can solve this equation for A, the lattice constant, A equals square root of 2 times the AX bond length, and we'll call that value A prime. Here we go, A prime. Right? That's one way of defining the lattice constant. Another way is going across the body center this way. So that's 2bx bond lengths. 2rx plus 2rb equal to the lattice constant. We solve that, of course, right? It's already solved for A. We take the factor of the 2 out. A equals 2bx bond lengths. Now we call that A double prime. Right? Why are we calling them A prime and A double prime? Aren't they just the same thing? Well, ideally, yes, they are the same. In an ideal cube, A prime equals A double prime equals A, the lattice constant. But in general, you might be surprised, A prime is not the same as A double prime because perovskites aren't perfect. So we have something called the tolerance factor, little t, and that's the ratio of A prime to A double prime. It was first derived by Goldschmidt about a century ago. And this isn't actually the way he defined it, but this is mathematically identical to the way he defined the tolerance factor. Okay. Boom. So lots of other things that can happen with perovskites generally. I won't talk in our modeling a lot about tilting, but just to introduce the subject, perovskites generally exist in non-cubic tilted forms, which means the octahedra, I don't know if you can see my hands, they tilt like this, or like this, about an axis. They've got 3 pseudocubic axes. They can tilt about any one of those 3. So some specific examples. This here is an example of one in-phase tilt axis. So there's a shorthand for these tilts. You don't really need to know this, but the 0 up here means untilted. So it's untilted about this axis, and it's in-phase tilted about the c-axis. So if we look down the A or the B, we essentially see nothing. You can see one of the oxygen vertices moving a little bit, but there's no tilting of the octahedra. Whereas along C, you can see, I think, there we go, you can see that there is tilting. It's in phase because, remember, these octahedra are stacked along the C direction, and I only see one octahedron. Right? So the ones below are tilting exactly the same as the ones above. They're in phase. They're tilting exactly in the same way as the one above and below. The other thing to notice here, it's kind of more subtle. There we go. As these octahedra tilt, you see how they grow? They're small here, and then they grow, right? And they get smaller as you untilt, right? So that's actually important because as the tolerance factor goes down, these tilts increase. And the reason they increase is because when tolerance factor goes down, it generally means the A site is getting small. If the A site gets too small, and this space that they occupy is too big for it. So the octahedra tilt to take up some of the space. That's how the structure is linked, like that. Another example here, this phase is one in-phase tilt axis and one antiphase tilt. So antiphase, you can see it in a second if it when the animation resets itself. You can see, there we go, there's the antiphase. You see the octahedra tilting in opposite directions along that axis. That's the c-axis. And they're tilting in the same direction along the b-axis. And they're not tilting at all along, that's the a-axis. All right, so we have one untilted axis, one in-phase tilted, like this one, and one antiphase tilted, like that one, like that. Okay. And then finally, something else, it's not really finally, but for my slide, finally, what can happen is distortion of the octahedra. So there's no tilting involved. This shorthand, if you understand it, tells you there's no tilting about any of the axes, but it's still not cubic because they're distorting. You can see how they're distorting, right? So there's another example of what can happen with our process. So in general, they are not cubic, and in general, they are tilted. And the lower the tolerance factor, so basically the smaller the A site, the more tilted they're going to be. Now this figure was published by Ian Rainey and his friends back in '94. It's done the rounds since then. It's a good general way of looking at the tilting of perovskites. So up here, up here, we have an untilted phase field where tolerance factors are pretty high. They're generally above 1, say, right? A bit above 0.985 or so. They're untilted. Now, it doesn't mean they're cubic necessarily, because some tetragonal perovskites will be untilted, but stretched into tetragonal unit cells because of things like lead giving you the Teller effect or something, right? So, and then once we surpass a threshold that's around 0.985, we get an antiphase tilted phase field. And then below about 0.965, we get the in-phase and antiphase tilting. Now, there are some exceptions to this, and it's not an absolute rule, but it's a good rule of thumb. And it's definitely the case that as the tolerance factor goes down, the degree of tilting increases. So you get much more heavily tilted structures down here than you would over here. Okay, so this is our, so properties, right? So, okay, this is the temperature coefficient of permittivity. This basically tells you how much the permittivity, or the dielectric constant, changes with temperature. Okay. For most devices, you want that not to change, or not to change very much, right? And the sort of mirror parameter, tau f, oh my goodness, it's not behaving for me. Here we go. There we go. Tau f is the temperature coefficient of resonant frequency. Again, you don't want this to change very much with temperature. Alpha here is the linear expansion coefficient. So these are related. Tau epsilon, tau f are related through the expansion coefficient. So that's how the tilting affects properties in a generic hand-wavy sort of way. All right, so let's look at our modeling. If we use A prime to calculate the lattice constant, then we get a curve like this. I've used, there are 132 data points along this line, this curve here. And this is the error, percent error in the calculated lattice constant. Right? So if A prime were perfect at calculating the lattice constant, we'd get a line at zero error, right? But we don't. We get this positive sloped line, basically, right? Which means our AX bonds are stretched, and we have a decreased A site bond valence because of that. And over here, on this side, we have a compression of the AX bonds and an increased A site bond valence over here, right? So decreased bond valence, increased bond valence on either side of T equals 1. And of course, when T equals 1, the error is essentially 0. If we use A double prime to do the same thing, we get this. We get the green data points. It's almost a mirror image, not quite. And we get the opposite effects. Using A double prime over here means we have a compression of BX bonds and an increased B site bond valence, and the opposite over here, stretching of BX bonds and a decreased B site bond valence. So, we looked at this back in 2007 and said, what if we just averaged those? Wouldn't they average out pretty much to 0? Well, you can do that, and they average out close to 0. You get a better fit, but it turns out you can do even better than that. This is the average, right? If you use the simple average of A prime and A double prime, you get an average absolute error of about 1%, 0.988%. Right? And there's the equation that would describe that situation. Right? That looks pretty good, right? Less than 1% average error, that looks pretty good. But what if, instead of taking a simple average, we do a linear regression in 2 variables? That's the orange data points. If we do that, we get a slightly better result, 0.768% average absolute relative error. And then we do something a bit weird. We put everything in 6-fold coordination. We assume. We use 6-fold coordinated radius data, anyway, from the Shannon tables, and we get the best result of all, 0.6%. That's the dark, this is getting confusing now, but you have dark blue data points on here, right? Hovered around the 0 error line. And there's the equation for that. So that's the best result we achieved for ABX3 Perovskites. So you graph those 132 data points, and you get this, what I think is a beautiful line fit. Here again, here's the equation that describes it. The average absolute relative error is 0.6%. We put everything in 6-fold coordination. Now, we're not saying everything is in 6-fold coordination. We're saying we're just using those data points. Number one, if anyone is familiar with the Shannon tables, it's difficult in some cases to find 12-fold coordination values, but more importantly, they're not known to the same precision as the 6-fold. If you look at all the cations on the Shannon tables, virtually everything exists in 6-fold, and then you often get other coordinations as well, because the radius varies with coordination, in case you didn't know that. That's important. So the 12 folds are just not known to the same exactness as the 6 folds. So we just use the 6-fold numbers and it works. That's all our model is saying, right? It works. Not saying it's right, but it works. Okay. Now, like I said, those were for A, B, X3, stoichiometric perfect Perovskites. Everything has some vacancies and defects because of thermodynamics. That's true. Okay, but the stoichiometric defects, they're not there, right? So how do you account for example, engineered in A site vacancies when they exist, right? So the point is you can use the Shannon tables to find the sizes of almost everything on the periodic table, but what doesn't appear on the periodic table is vacancies. So how do you calculate the size of a vacancy? It's not 0. It's almost never 0. So what's the size of a vacancy? That was the problem we encountered next. So in order to tackle that problem, we go back one little step away from our everything's in 6-fold coordination model, one step back to everything's in the right coordination, right? So it's not the best fit we had, but everything is in the right coordination. Because when we start playing around with things, we want things to be in the right coordinations. So this was the equation that described those orange data points, where we did the regression in 2 variables, but everything was in the right coordinations, right? It gave us a good fit, 0.7, I think, slides back. So from this equation, we can define the tolerance factor by solving it for the Goldschmidt tolerance factor. But in this case, when we do that, of course, we get this, right? Because we're rearranging this equation. So we get this. So I call this T prime because it doesn't look identical to the Goldschmidt. Why would we recalculate the Goldschmidt tolerance factor? It's a different way of defining the tolerance factor, and it's actually much better at predicting structural effects, which I won't go into too much, but it's another way of calculating the tolerance factor, but it's not Goldschmidt, so I call it T prime. So you can use this equation to calculate the lattice constant in terms of T prime. So we're just rearranging this equation, and PC is pseudocubic. So the pseudocubic lattice constant is this now. It's a function of T prime and the Bx bond length. So we require B, which we can get from the Shannon tables, easy. The ideal, which is the Shannon anion size, we can get that easily. And of course, we need T prime. To get T prime, we need the lattice constant. So the problem here is that we don't need RA. So the problem of what's the vacancy size goes away. We don't need to know RA, but we do need to know the lattice constant. So we can't use this as a predictive approach. We can check things, but unless we already know T prime by experimentally measuring the lattice constant, we don't know enough to use this equation. So we need a different approach. So what we've done, our model starts with, first of all, RB, the B site, is what Shannon says it is. And there's no reason to doubt that it would be. We're not adulterating the B site in any way. So the first and only assumption is that the B site behaves the way Shannon says it would. And then just from geometry, the anion size is half the lattice constant minus the B site size. That's just from geometry of a cube. And if we do that, we plot Rx from experimental lattice constant measurements, and we should get for Rx over Rx ideal for this guy here, Rx over Rx ideal. Rx ideal, remember, ideal means Shannon. So it's the Shannon size. If Rx were the Shannon size, this would just be a line here at 1. But it's not quite, it's still a line, but it has a small positive slope. And the equation that describes it is over here. All right. And down here, we have RA minus RA ideal. So RA from geometry, this guy here, right? Just from the geometry of a cube, minus the Shannon size. So if RA were the Shannon size, this would be a flat line at 0. The difference would be 0, right? But it's not. It has this negative slope. It's almost a line. You can pretty much describe it as a line, but it fits better as a quadratic. So we fit it as a quadratic. This is the equation that describes that red curve. And the idea here is that as the ratio of cation to anion size approaches the critical value for anion-anion contact, approaches from above, repulsion from the anions increases and distends the apparent radius. This is a really important point. I'll show a graph about this in the next slide. But here, so what I'm saying is that the radius is a function of this ratio. And this ratio is neatly summed up in the tolerance factor, because that involves both A and B, or A and X rather, A, B, and X, in fact, all three of them, right? So this ratio is neatly tidied up in the tolerance factor. So the radius should be a function of tolerance factor. That makes sense. Now I'm going to try to prove that to you, maybe more simply. I don't know. These four compounds all have the sodium chloride structure. They have the same structure, right? If you use the Shannon tables, this is the ratio of cation to anion size, right? This is the sum, so this is the bond length, cation anion, right? Now, according to Pauling's rules, he has this ratio rules. This should be an 8-fold coordination. These two are correct, and they're 6-fold, and this guy should have 4-fold coordination. But they don't. They all have 6. They're all in the sodium chloride structure. If we look at the observed bond lengths and compare them to the what Shannon would say, add up the ionic radius values, you can see that for a large ratio, rubidium bromide, it matches really well. But as we go down the list, deviations start to appear, right? And finally, down here for lithium bromide, when the ratio is really small, there's a large discrepancy, right? 0.2 angstroms discrepancy. And what's going on? Why does the discrepancy increase as that ratio goes down? It's because as the ratio goes down, the anions are getting closer and closer together. And Shannon's rules were developed assuming neutral hard spheres. Atoms were marbles, basically, right? The problem is atoms aren't marbles, and the outsides are not hard, and they're not uncharged, right? You've got a cloud of electrons on the outside of your atoms. They're the ones that are going to be touching, and they're not going to touch, right? So if they approach too close, they start to distend, and it effectively makes the anions look, and the cations too, look larger than they are. So you get larger bond lengths in reality than Shannon would tell you you would have. And my student did this graphically for me here. So rubidium bromide up here, there's no discrepancy, and as you go down in the ratio, the discrepancy opens up quite a lot, right? So here's Pauling would say the critical value for the radius ratio is 0.414, but it doesn't work in reality. Pauling's rules often don't work in reality. But the important here is that the size is a function of the ratio. And that's exactly what we're observing. And it shouldn't be new because this was published in a book from the 60s, right? So it's been known for a while. It's just often ignored, and sometimes people aren't aware of it. Okay, so what we've done here is we've got several families of rare earth doped divalent titanates. So calcium, strontium, lead, or barium, lanthanide doped titanate. So the lanthanide series were lanthanum, cerium, neodymium, and yttrium. And it almost doesn't matter because all of these guys, it seems, which I was astounded when I saw this, they all form on the same lines for a given divalent species. You get just 4 lines here, not a bunch, right? So this is a very key figure because it shows us, number one, that they are all on lines. So it doesn't even really matter which rare earth you use. And because they're all lines, all you need to do to define a line are 2 points, right? So this point is in common for all of them. This is x equals 0.1, a third. X equals a third. So there is no divalent species here. So this point is shared by all of these compounds. This is basically lanthanum titanate. It's kind of a virtual compound. It exists in the literature, but I think in recent talks with colleagues, I think it doesn't really exist, but it exists virtually enough for us to put it on a graph and use it as a data point, as an extreme data point. And then what we have are a spread of data points here on the intercepts. So if we can develop a curve fit for the intercepts, then we have this data point. We always have this data point. We've got 2 points. We can define every single line. And that's exactly what we did. That was our process. So we did a curve fit for these intercepts, and that's basically this down here. T0 is the tolerance factor for the x equals 0 composition, if I remember correctly. And then the slopes, from the slopes, we get something to do with the vacancy size. So that's where this term comes from. Again, T0 is the tolerance factor when x equals 0, and x is the concentration of vacancies. It's the x from here, right? Which is the concentration of vacancies. It's identical. When we formulate this way, x is vacancy concentration. So this bottom equation is the important one. The A site size has 3 components. It has the Shannon, whatever Shannon says it's supposed to be, the ideal size. It has this term, which comes from this intercept, which we call a bond deformation. I don't know if that's a good term. It's what I've been using for the past 5 years or so. That's what's called the bond deformation term. And over here is our vacancy size term. So if there are no vacancies, this goes to 0 because x is 0 and this vanishes then, right? So 3 components: Shannon, bond deformation, vacancies in general are the components of the RA. All right, let's move along quickly. So you can graph the size of vacancies. This is our equation for vacancy size. And there's calcium titanate, was calcium vacancies, about 1.3, so about the same size as calcium, actually. Strontium, magnesium niobate, PZT, strontium titanate, lead titanate, barium titanate, in almost all cases, apart from calcium. In fact, it's for some calcium cases, but not in all. In all of these, the A site vacancy is larger than the A site cation it replaces, which means the cation vacancies have a pushing effect. So far from being the size 0, they actually look like they're bigger than the cation they replaced, right? You get repulsion. You think about that, you take a cation out. The cation was coordinated to anions, which now just see another anion across the vacancy, right? And so they repel. And it looks like when something is big between them because of the charge. All right. So how do you calculate the tolerance factor when there are vacancies present? This is an example we did for cerium-doped strontium titanate. If you assume that vacancies have no size, you get this crazy deviation here from our perfect fit line. Right? So clearly vacancies have a size, but what do you use for T in this equation? Right? If you want to calculate a lattice constant for something with A-site vacancies, you need tolerance factor. What do you use? If you use tolerance factor without accounting for vacancy size, you get these crazy large errors. If you use RT prime, that works great, but of course you need to know the lattice constant first. So it doesn't work so great. So what we need is a relationship for T prime and T. We need to relate T prime to T without knowing lattice constant first. So we've got these curves. They look similar, and they are similar. They're all quadratic. It's on the slide. Oh, there we go. They all fit a quadratic form. T prime is a quadratic as a function of T, the Goldsmith tolerance factor. So what we need to do is get a fit for the ABC coefficients. So I know there are a lot of coefficients in this talk. So we got to talk for a fit for the ABC coefficients. They're all quadratics if you graph them with the size of the divalent species when x equals 0. So A, B, and C, we can plug in these values from Shannon, and so we can get T prime as a function of T. Now we can do that. We can use our model to go forward and calculate lattice constant. So I'm going to summarize the first part of that model here. B is the Shannon B. RA has 3 components: Shannon, bond deformation, vacancy size. T prime is a function of T, and these are its lattice coefficients, A, B, and C. And once you know T prime, you can stuff that into this equation for the anion size. And once you know that, you're off to the races. You have 3 ways you can define lattice constant then: using T prime, using A prime or A double prime, which uses the AX prime or BX prime. All right? So that's a nice, handy summary of the first part of our model for A-site vacancies. When we apply it using the T prime as a function of tolerance factor, we get this equation, we graph it, we get this. The average error is 0.33% for the Perovskites I showed you on the other graph that we derived it for. But remember, we get 2 other ways of calculating lattice constant. We have A prime and double prime still, right? So we can do a linear regression again and graph A as a function of both those things, and we get an average error of just 0.15%. Okay. Now, a couple of facts, structural facts I talked about that we can see from this. First of all, I've graphed here A prime and A double prime for these Perovskites, right? And one thing you notice is that the fits are very good, but all the errors are slightly positive, right? With one exception. The exception of these green data points, which are the lead, lanthanum, titanate data points. Right? So keep in mind, A double prime involves the BX bond length. A prime involves the AX bond length. So because BX looks good, everything looks consistent, but this is the inconsistent part here involving the AX. This strongly indicates that there's something wrong with the A site size in this for this composition. And if we very slightly alter the A site size, we just add 0.168 angstroms, a tiny amount, 1.1%, to the size of the lead, we can eliminate those errors. And I think that's evidence of the second order Jahn-Teller effect, something called the lone pair effect that lead, everyone knows, has because of the electronic configuration of the lead 2+ cation. And we see the same thing if we include lead lanthanum zirconate titanate, so PLZT. We did some work on this too. Again, A prime, A double prime. The only negative errors are here for the lead compositions. If we add a little bit, in this case 0.0415 angstroms, 2.8%, we can eliminate those errors. So again, I think that's a way of quantifying, in some way, quantifying the strength of the lone pair effect. Now let's look at B-site ordering. I'm going to run out of time if I don't get a move on, I think. B-site ordering, right? So there's a bunch of perovskites where the B-site is shared in an ordered way. So magnesium and tantalum, in this case, share the B-site in a 1:2 ratio. All of these have a 1:1 ratio. The point here is that they all have very large errors. Remember, our errors are much less than 1%, right? We're talking about 1/3 of a percent or even less. These errors are huge by comparison. So what's going on? Well, it turns out if we can correct the B-site size in this case, we can essentially eliminate those errors, right? Now they're mixture positive, negative. They've basically been eliminated, and all of these corrections are negative. So we've shrunk the B-site size. Right? What that means is when things order on the B-site, they shrink. And you'd expect this. Ordered things stack more efficiently, pack more efficiently, so you'd expect them to shrink upon ordering. And that makes sense. It explains a lot of things in material science. We did DFT, and we did prove it, that the ordered form, in this case, we used the lanthanum zinc titanate compound, which orders. We simulated an ordered and disordered, and the disordered form has a larger volume than the ordered form. So it's true, B-site ordering involves a volume shrinkage, and that shouldn't come as a big surprise, and we just quantified it. Lots of examples. This to me looks like spaghetti strands. One of my students showed this to me. But again, these are all quadratics as well. They all fit this sort of structure mathematically. So these are the ABC coefficients in this case. So now, of course, a lot of coefficients. We need fits for the ABC coefficients. And luckily in this case, these all kind of look the same, like one big curve. They're not independent, right? B is a function of A, C is also a function of A, and therefore B. So we can simplify things a little bit, and we get the ABC coefficients have this sort of form. This describes these curves. And for little ABC, you stuff in these coefficients here. So we can calculate ABC, which means we can calculate the rest of it. And when we do that, we have the result down here. So the blue data points are without accounting for the B-site ordering. The orange data points, where we account for the contraction caused by the order. So that works. I'm going to move along. Now, what about A-site ordering? For the A-site, well, we first started doing this with sodium lanthanum titanate, which was an interesting microwave material, well, about 12 years ago, I guess now. This was first published. And it's because the microwave data looked promising. You had kind of large permittivities, which looked good. And since you have such a large permittivity, you have lots of room to engineer this. If you have to sacrifice some permittivity, you had it there to sacrifice. You had kind of large quality factors. That means you have low losses. The temperature coefficient looked a bit large, but it was also coming down. And you think, well, you could play some chemical games maybe and reduce this a bit further. So it looked like a promising material. It was published as a disordered perovskite, so there's no ordering on the A site is what was published. Lots of models showed that. So when we looked at it, we calculated a bond deformation. It was negative, which meant the AO bond length was less than the ideal Shannon line. A vacancy size of 1.6379, which pushed because that's bigger than either sodium or lanthanum. So the result was a push, as we saw before. The interesting thing here is that we saw as the vacancy concentration increased, the lattice constant also increased, which seems counterintuitive to start with. Vacancies are increasing, but the lattice constant is also increasing. It's because of this. Right? Tolerance factor, T prime, was also increasing, which meant the degree of tilt was increasing this way. And it all made sense. The model made it all make sense wonderfully. But the problem was still with the ordering, right? So we look at this again. Here's our several compositions of sodium lanthanum titanate. X equals 0 is the one-to-one perfect order, and then we deviate from that. Here's our lattice constants, right? A prime, A double prime. Our errors, again, these errors, they don't look huge in themselves, but they do start off largely negative and become more and more positive as you go on. That is the telltale sign of an underestimation of the AX bond length. So we correct this, again, with A site corrections, positive, so we're expanding the A sites this time. And we get our errors to go away. So this was the peculiar thing that we saw about the ordering. I didn't even know what to call this to start with, because ordering was causing an expansion of a cation size. And that didn't make sense to me to start with. Why would you have a volume expansion on ordering? It's not what we saw on the B site. But we did DFT, and however you model these in a tetragonal or a trigonal structure, you always get the disordered form has a smaller volume than any of the ordered forms you can do, either laying on 001 or 110 or 111 layers. Perovskites are known to layer in all of these ways. The A site normally this way, but not always. No matter what you did, you always got that ordering caused a volume expansion. So this is a real effect. We did work it out later. I'm not sure I'll have time to explain it today. And the funny thing here is that this is our X-ray data, and this is why people publish this as disordered. This is sodium lanthanum titanate, X equals 0, the stoichiometric composition. There are no ordering peaks here. There are no ordering peaks here. They don't appear until X equals 0.1733. They start to appear. So what this is telling us, it seems, is why, well, the question is raising is why is there no evidence of ordering when there should be ordering, right? You'd expect ordering to be best when you're nearest the ordered stoichiometry, a one-to-one stoichiometry. And worse as you go away from it. But that's not what we were finding until you look. What we're seeing here, it's not no evidence of A-site ordering. What X-ray is showing us is there's no evidence of long-range A-site ordering, right, at those low X values. If you look in electron diffraction, aha, there's the ordering, right? All these diffuse spots are ordering, but they're short-range ordering. You have nanodomains of ordering now, right? So you have good ordering, but on a very small scale. So the summary here is that at low X values, you have most grains with order, but they're nanodomains. So it's a very short range, a good short range order, so the diffuse spots. And as you go up in X, you deviate from the perfect ordered composition. So the degree of ordering decreases, but the extent of ordering increases. You get long range order now, but just of worse quality. So you get more discrete spots, but they're still weak. So that's what's going on. And in interest, I'm going to start to speed up a little bit. You've got ordering parameter, which is a line. You might not be surprised. It's a linear ordering parameter. When X equals 0, you get the perfect order, and X equals 1/3, you get 0 order. And we can do a curve fit for that, right? So whatever RA correction you need to put in, stuff that in this equation, it tells you what the ordering parameter is, right? So that was kind of cool. We did the same sort of work with lithium lanthanum titanate. There were way more data points. We didn't make any of these, all from the literature, but it emphasizes the point even more. This stuff is reported with long-range A-site ordering. And you can see, again, large negative errors at low X values that increase the positive as you go up, right? Same thing here, right? So classic, we're underestimating the AX bond length. We correct it with an A correction, and the errors essentially go away, right? And all of these are positive, large to start with, and less as you go up in X. Same sort of thing. There's our ordering parameter. We can stuff in the delta RA that's required, and out pops the ordering parameter. Cool, nifty. All right. So, okay, we made a bunch of intermediate compositions to show that we could do this generally, and we can. Again, lots of coefficients involved, so you'll have to forgive me, but it works. We have, again, they're not all independent either. I think you can tell that. So we have delta RA equals this, and the important thing here is the ordering parameter generally is this guy, and the ABC coefficients come from here. You just stuff in the ideal A site size for the x equals 0 composition. So these are, you can plug these in right away. These are just constants, and out pops the ordering parameter for any A site ordered material with the, as long as you know the delta RA is required. Okay. Sorry, I'm rushing a little bit. We have materials, a few, that have ordering of both A and B sites. So we have these guys up here. And so we'd expect, again, correction factor is positive for A, negative for B. And the errors actually do identically go to 0 because you have 2 parameters to play with, so it's pretty easy to make them go to 0. Okay, now let's look at oxygen deficiency. The last thing I want to talk about, but it's important. Oxygen vacancies can cause either volume shrinkage or volume expansion, very commonly both ways. We used calcium titanite ferrite and strontium titanite ferrite. We got single-phase materials. In this case, there's a phase change happens here from orthorhombic to tetragonal. These are all tetragonal. But the important thing here is from geometry, this is the same equation we had before, if you remember, many, many slides ago. But now we're solving for Rx instead of Rb. And we have this, all right? So this is Rx over Rx ideal. Again, if Rx were equal to Rx ideal, this would just be a line at 1. But it's not. It's still a line, but it's got this positive slope, just like it had before. And remember, the last model had this. These are essentially the same equations. We're using a different data set, so the number, the equations come out very slightly different, but the actual values come out virtually identical. So that's the same equation. And from stoichiometry, we have this. These are the 3 components. So this is the ideal Shannon contribution to the anion size. This is our bond deformation contribution. This is the contribution from anion vacancies. We solve that like this. This is all, we just call this y. It's all constants here. This is the equation of a line. Y equals mx plus b. So the bond deformation, which I'm now calling dB, is 1/6 of the intercept, and the vacancy size is the slope of this line. So we graph these lines, and there we go. There's all the lines. There's all the values we found. Now we need to generalize this. So again, we've generalized it. This is vacancy size. This is bond deformation. We've graphed these as a function of t prime when s equals 0. Let's just remind you. And off we go to the races. And we have, remember, t prime is a function of the x ideal. And these guys, these are just a line, right? These are our lines. T prime. I couldn't do t prime versus, oh my goodness, what's going on? There we go. T prime versus x ideal, right? So these are all lines. This describes the lines. We need the AB coefficients. Here are the AB coefficients. Here are the AB coefficients graphed against this weird, I don't know, my student invented this weird geometrical term. It's just a constant though. And you stuff it into these equations and you get A and B. And again, these are essentially mirror images of each other, so they're not independent. So you can describe B in terms of A, like this equation down here. And bottom line is you can describe then the lattice constant as a function of this t prime value. And you get a nice curve fit, right? Calculated versus experimental lattice constants. So I know I have to rush through that a little bit. So my conclusions, the effective A site vacancies and anion vacancies on unit cell volume and the effective size of those vacancies can be modeled via these correlative equations. The effect of the Jan-Teller distortions, second order Jan-Teller distortions, can be quantified. We can't predict them yet, but I think with a bit more work on more compositions, again, for correlative models, they're all empirical. You need data to create them. So with more data, I think we can probably do this. B-site cation ordering, rock cell ordering results in the volume shrinkage with respect to the disordered structure. The A-site cation ordering, which is a layered ordering, results in a volume expansion with respect to the disordered form. The degree of order, even short-range order, in this stuff can be predicted by the RA correction required. And even simultaneous order on A and B sites can be modeled and the degree of each determined. So with that, I'm going to thank you for your kind attention. I'm also going to thank my 2 previous PhD students, who is now my postdoc, and Kevin Tolman, who is now a postdoc at the INL. This is the Idaho National Lab. And Bing Liu, who was a visiting PhD student from Zhejiang University several years ago, and his supervisor, Zhengmin Chen. So I will leave it at that, and I guess I am open for questions for however long you guys have.
Professor Rick, actually some questions are already there in the chat box. Maybe if you can see the chat box, you can answer them.
Let me see chat. Okay. So B-site vacancies. Someone's asked about B-site vacancies. I'm just going to go in order. So we did some work many years ago with B-site vacancies. It didn't go that far because we had great difficulty engineering enough B-site vacancies into perovskites. They're not generally that stable. So that work, there is a paper or two that our student did publish. I can send you a link to it if you really are interested, but we didn't get very far with B-site vacancies. They're not nearly as common as A-site and anion vacancies. So I'm sorry if that lets you down. How to calculate relative error in A prime and double prime. So error is very simple. You have to have an experimental constant measured, and then it's just your calculated A prime minus the experimental divided by the experimental. And then we just make an absolute value, and we take an average. So it's the average absolute relative error. That's how we calculate those errors. So without the experimental data, you don't know what the error is. So I'm not sure if that's where the question was coming from or not yet. To get those errors, we need the experimental data. These are all empirical correlative models. They're all based on real data, which is what I started from in the beginning, saying these models might not be right, but they work. All these models are based on real experimental data, so they actually work. The numbers that come out are very close to real experimentally measured values, right? So we go around the theory a little bit, but we get to the real workable data in the end. Curve fitting. My student used, I think he used Mathematica. He used Mathematica for the curve fitting. And how we came up with some of those forms for those functions, I think it was just luck. He tried a bunch and he showed up with ones that worked. It was Mathematica, though. He was far more adept at using Mathematica than I ever became. I would just use Kaleidograph, and it has much simpler curve fitting tools on it. Couldn't do all that. The DFT calculator were all done. They were all done using VASP, I think. I'll have to check the paper. I'm pretty. They're all done using VASP. No, it's not. No, yeah. I'll have to check the paper. What these for DFT? It wasn't my group in the DFT. A collaborator did that for us, and it wasn't. Was it? Oh, I'll have to check. I can check that. I can check that, and I'll send the answer to Subodh, and he can pass it on. A-site ordering. So A-site ordering from electron diffraction, any kind of ordering, if it's long range, even short range, in electron diffraction gives you superlattice reflections. So you see the fundamental perovskite, we know this very well. If there are frictions between the mental reflections, there's our superlattice. And it's caused by either ordering or tilting. So you have to kind of know how to interpret. Certain ones are caused by orderings, some are caused by both. You have to know how to interpret, but that's how we do it. Lattice reflections. And those are, I showed you some on that slide. I have only two slides with electron diffraction. Some are diffuse reflections. Those diffuse reflections were the ordering reflections. And on the next slide, some were diffuse and some were just discrete. Those are all ordering. To verify the presence of. So anion vacancies. That's a good question. The way we did it, we formulated compositions that would have anion vacancies. We synthesized them, and then I should say that we synthesized some, but the most success we had with our collaborator in Slovenia, who synthesized most of them, and he would just make them. I don't exactly remember how he did them. It's in our paper how we did it exactly. But basically, we produced them. If they came out single phase, they were what we got. So basically, our they're engineered to have vacancies, and some of them were from literature. So like we're completely making something up. They were based on reality, and we just used the same family to create more data points in the same family. And as long as they came out single phase, they were what we set out to make. Okay. Did I cover all the questions completely enough for you? I know I was kind of quick.
I have a question. Yeah, I have a question.
Yes, please.
See, when you are coming to quantum dots, what will be the structure?
Oh, good.
Perovskite quantum dots are there now in use.
So I'm gonna bypass that question. So our modeling requires that the kind of defect is completely, we have homogeneous materials. The materials are homogeneous. Any defect is randomly distributed throughout the medium. So as soon as you get something that breaks that assumption, all bets are off. So I can't really answer your question. I guess I could conjecture, but I can't really answer it. Our modeling doesn't do that. Our modeling requires that if you have a certain concentration of vacancies or a certain degree of ordering, it exists throughout the sample, throughout the material. So I'm sorry if that disappoints you. That's the best I can answer. Our model isn't that good.
So any other questions?
I'm sorry I had to rush it in. I thought I had it. I didn't actually send it, but I thought I had it the right time based on what I gave the MS&T talk last month. But I guess I was a bit.
Rick, I'm Surendran. I have a question.
Yeah, KP.
Yeah, this is regarding that the superlattice, structures that you have made, the slides that you have shown in the beginning. How do you control the island formation in superlattice generation?
So again, we make no effort to control. We produce something, we get the X-ray, and we assume that everything is uniform. Okay. And we get beautiful fits. So I think the assumption is pretty good. But if there is a any non-uniformity, degree of ordering, whatever it is, our model can't really get to it, or it'll confuse the model, I think. But I don't think we've seen it because our data points are really, really very, very convincing.
Yeah, like very one-lattice reflections. Yeah, fine. Yeah. Thank you.
Yeah. You can localize the effects of any kind of ordering of defects if you use electron diffraction. You presume very small probe size, right? But our model doesn't get to that sort of scale. I guess you could apply the model with different assumptions for different parts, but the model is based on X-ray input, right? So you need a lattice constant, and X-ray is not site-specific. It's a massive thing.
Okay, thank you.
Yeah.
Rick, there has been a lot of interest in the hybrid perovskite. So have you tried to this kind of things?
We're actually working on that now. Actually, where I started before my talk began. That's my student who's severely ill. He's working on that now. So he's not doing as much work now. But yes, I did several years ago. I had a go at using our model such that we had it back then. This was in 2016 or so, to calculate what I thought the T prime would be for the methylammonium lead iodide, right, that everyone was using at the time for these things. And it seemed unrealistic to me at the time. I remember thinking, could this even be a perovskite? It didn't seem real. But that's as far as I got with it. I think we can apply. There is some question about how applicable the Shannon sizes are for the non-oxygens, right? For the bromides, the iodides, the chlorides, how reliable those values are. And I've seen a paper in the last year or two that attempted to redo those anion sizes because the way, I can't remember how Shannon derived them, but they weren't as reliable as, I think he derived, I don't know how he derived them, I don't remember now, but the paper was arguing that they weren't that reliable. So it's possible the data I was using was from Shannon, wasn't that good for those compositions, and that's why I was getting these unrealistic tolerance factors. So there's a question there. I think it should work. There's no reason why it shouldn't. The data that I showed you, the first curve, the first line with the 130 data point, was for ABX3, and X was generally X. There were hydroxides there were chlorides, there were all sorts of things in those data points. So there's no reason why that at least shouldn't work, as long as you can work out the sizes for methylammonium or for formidinimo, whatever you're using on the A side.
Okay, Rick, one more question regarding, since this is empirical modeling, how about predicting new perovskite using these kind of models?
Really good question. So what our model can do is get trends. The model is very strong for trends. So you get an equation, you can just vary it smoothly, continuously, right? And find trends interpolating through data, and even some extrapolating. Empirical models aren't good generally for extrapolating because you're only really valid between the limits that you've measured, that you have data for. But you can get trends released. That's the strength of these models. Predicting entirely new compositions is possible. Well, that's where we'd like this to go. We'd like this to go more than just structural predictions, but property predictions. And one thing I haven't shown you is we've done work on structurally modeling non-cubic distortions. So we've done tetragonal distortions, quantifying those. Trigonal distortions is the latest one we've done. These are very simple distortions where it's still ABX3. You haven't doubled or tripled anything. You're just slight distortions along 001 or 111 of the cube. I'm not thrilled with the quality of those. They're good, but they're not. They have problems. Those fits. What we have done, as soon as you do that, in most cases, you generate a polarization, and so you can calculate a curve for intrinsic polarization, which relates to permittivity, right? So you can do property measurements, property calculations, predictions this way to a very small extent so far. We've done this with polarization with those two. It's possible to get a triangle distortion without polarization. Those is just two. That's space root P4 upon mm. You get no center. You get a center of symmetry. You get no polarization. But predicting new materials, I think, is possible with using the power of the trends. That our equations give you trends. And if you said, well, if you can extrapolate with a property, you got a property, you want a property here. Okay, you need a structure here. You can use our model to say, okay, well, that means I would need an A site like this and a B site like this. You can do that because of the, like I said, the power of the trends. We get an equation that describes, X versus Y, right? We get an equation that describes a structural parameter versus some processing parameter, right? Composition on the X and size of something on the Y or something like this, right? So yeah, I think we can do that. We're not there yet, but I think that's definitely one of the strengths of this modeling technique is trends. You can easily calculate trends. Like I said, it's all done on an Excel spreadsheet. So.
Okay, any other questions? You can also type in the chat box if you have any other queries.
I can't believe I don't remember the DFT software. I'll check it and I'll send it to Subodh. I've just I'm blanking on it now. It's okay. I'll double check it. Sorry, I don't do it.
So if there are no queries, I invite Adira to say formal vote of thanks. And I also request Professor Rao and Professor Unikrishnan Nair, Professor Gopchandran Nair to stay online.
Thank you, sir.
Adira.
Yes, sir. Yes, sir. Honorable dignitaries and most valued guests, it's my privilege to propose the vote of thanks on behalf of Department of Physics, University of Kerala on the occasion of its Golden Jubilee celebrations. We want to express our sincere gratitude to our honorable guest, Professor Rick Ubic, who has spared his precious time for us and enlightened us with his knowledge. I extend our sincere thanks to all other distinguished guests who graced this occasion with their presence. A warm thanks to the organizing committee, especially our HOD, Dr. CBKs, Dr. Subodhji, Dr. V. Biju, and also I would like to acknowledge the immense contribution of all other dedicated faculties of this department. Finally, in the end, I would extend my all-other gratitude to all the participants of this webinar. Thank you all for making this program a huge success.
Thank you, Rick.
Thank you.
Thank you.
Rick, Dr. Sebastian is also online, Rick. Dr. Sebastian is also online.
I know his name, yeah. I can see the top of his head.
Hi.
Hi, Sebastian. How are you?
I was a little bit late.
For a long time. I visited Kerala, gosh, was it 11 years ago? No, long time ago.
2010 or 11. I think 10.
10 years ago then.
Yeah.
I enjoyed it. Some of the work I present, I should have said, some of the work we did actually in collaboration with Sebastian, the cerium doped strontium titanate. We've done lots of work with you over the several years, haven't we?
And also on appetite.
That's right, with the appetites.
Yeah.
Yep, lots of work on things. Very interesting. You kept my research feel very interesting. Interesting things to look at. I enjoyed it. We're doing the RTF now. Did it? I remember I forgot to tell you. The proposal wasn't accepted as we submitted it, but it was supported as an eager proposal. Heli knows about it. We're working with we're using Heli and Yari as our advisees, but they wanted it pared down. They were apparently worried that we were over dependent on our collaborators, so I had to cut them all out. So it's cost us more because we have to buy a bunch of equipment now that we didn't have to before. But anyway, we've just started that in October, so it's making some good progress.
Yeah.
But the hope is to resubmit the initial proposal, because this is only 18 months of funding. We'll resubmit the initial proposal in about a year, putting you back on it as our visiting guy.
Yeah.
All right. So I shall leave now, I guess, and leave you guys to chat. Thank you very much.
Thank you.
I hope I did.
Thank you, Rick.
Thank you.
Okay. All right. Bye-bye, everybody.
Thank you, Rick.
Professor Rao, it is a long time. I am seeing you. Unixner, you unmute.
Sir, you can unmute your mic.
Yeah, can you hear me? Hello, Unikrishna.
Oh, it's a long time.
It's been a long time. Yes, indeed. How are you? How are you doing?
Here I am, Trivandrum.
Yeah, you're in Trivandrum. How are the other friends? Devanarayanan and Prabhakar Nair and
Both are here. Both are here. That is not come to join. That's all.
Oh, they're not online. Okay. It's very good. It's to see you in this meeting. It's indeed a great pleasure. I think the department is now started building it up. You probably should advise them as and when, and keep visiting the department. Dr. Subon, I thank you for sending me the mail and giving me this opportunity to participate in this, to listen to Dr. Rubik. It was a nice talk.
Thank you, sir.
And all the friends are also here. Gopchandran is here. Then the research students, Shanda, Sunil Abraham, all these people are here.
Oh, this
Gopchandran,
so
sir.
nice. Hello?
Gopchandran, unmute. Then Shanda is here, Sunila is here.
It's so nice to hear all those names. Some of them I have forgotten, but
Rao sir, I am Sunila Aruldas sir student here. Happy to see you after a long time.
okay.
Sunila.
It's so nice to see you.
Okay. I'm
very
also
good.
very happy to see you. Okay.
Excellent. I think this is a wonderful arrangement. The Kerala University, whenever they conduct conferences or invite somebody to talk, some eminent person to talk, please do send mails to me. I will be very happy to participate or listen to the talks and keep in touch with the department. I am so happy that Space Weeks is again going to be started pretty soon. From which year it is going to be started? The Space Weeks?
Sir, this year.
in the department?
This year, sir.
Actually, in 1970 it started with Professor
Oh,
Paul and joining. Now it's the
It
50th
started
year.
this year.
Yeah, 50th year.
Okay, it's good. I'm glad that hopefully I heard that some 40 research students are there. It's very good. I never thought that that big a number will be there. Some time ago, when I saw very few faculty members were there, and I thought I think the department has come down to minimum threshold level, and felt sorry about that, but I'm so happy that it is started building up, and it's probably rapidly building up. I think I wish all the best to the new and young new generation of the faculty there, and hopefully they will go far beyond what we could do 2-3 decades ago with Professor Vishwanathan and Arul Das, Krishna, ETH, and White and so many people, so many helped, and we had a wonderful students, and many of them have reached very high levels in the Department of Physics and elsewhere. Maybe I will have another chance to say a few words about those times. Maybe 15th, 16th, it seems there's going to be a celebration. Probably if I get a chance, I can say a few words at that time. It's good to be part of this meeting, and I would like to say hello to everyone, greet everyone, and be in touch. I think I was in touch with some of those old students who themselves were retired, retiring, and some have retired. I think, and of course, some are in different fields. Dr. Balan, I was in touch, and this people in not only in Trivandrum and Cochin also. Vikram Kumar is there. Like that, many, I think, Shyamala and Radhika Ramchandran, Raji, so many people are, they're about to retire in a few years and all that, but some of them are extremely active at the moment. It's so nice to talk to you all, and it's good to see you all. Thanks a lot for this opportunity. Krishnan, I hope I will see you again on and off with these video meetings. Good to see you. Say hello to Devanarayanan and other friends. Thank you.
We will meet at the next talk. Okay.
Rao sir, one request.
Tell me.
Yeah, actually, can you speak to our MSc students, the new batch, for some time, half an hour? Is it okay?
When? Right now?
Not right now. Not right now. Yeah, you can choose the time, date and time. You can choose the date and time.
All right. I think I can speak to them. The present MSc students?
Yeah, the just joined batch.
The space physics students.
No. That is set to start. It will be started in maybe in January only, because the course was sanctioned a bit late, so it will be starting in January only.
The present MSc students, what specializations?
They applied electronics.
Applied electronics. Okay. Oh, applied electronics. Well, that was part of the old course.
Yes.
Actually, in my time, in fact, actually, I was the one who started that terminology and also that course, applied electronics in space physics. And the space physics students said the electronics is an attractive term, so please do add electronics to space physics. So after 1 year, we added that term. It's called space physics and electronics. and the other one is applied electronics. 2 streams, and it was equally divided. And some bright students have gone to space physics, electronics, and some to applied electronics and all that. And some of them have gone to very high levels in the government and abroad and in various organizations, R&D organizations. Some of them I know personally. I have been in touch with them even today. It's good to see, including actually the very first batch. One Lakshman was there, and we learned many things together. Although I was a professor, he is a very dynamic fellow. He was the very first batch. I think that was in 1977 batch. He went to Wisconsin for computer sciences and all that. I could relate to some of those old times. Maybe in the meeting that you're organizing on 16th, was it? You were telling actually.
It was on 15th. 15th.
Oh, 15th. So I can participate in that meeting. I would like to listen to you people, actually the current activities, as well as some of the students. They could speak at that time. What exactly they want me to speak, and they would like to know. I can say I think the future looks great for both electronics and space physics. Things have changed quite a lot from my time. The opportunities have gone up enormously today in space sciences and technology, as well as in applied electronics as well. And so many educational institutions have come up. They should spread out, and I would like the bright among them to opt for the universities and the educational institutions, because that way it will be faster to build up the strength in the country in the science and technology. So thanks a lot. I am very happy to say a few words at this time, but at that time I would like to trace from the beginning of what I know, 70s, starting with Professor Vishwanathan, a wonderful academic. I was quite fortunate to work with wonderful people at that time, and that was the most memorable period of my career, and so rewarding. Thanks a lot.
Thank you, sir. Thank you.
Okay.
Rao sir, we the alumni will also join on 15th December to listen to you also.
What is that? Alumni meeting, was it?
Yes. Yeah,
When
alumni
is-
also.
I am here. I am Gopchandran. I am here.
I see. Okay. No, I will be most happy. Still, I think I would like to, unfortunately, all these years, even after retirement, I continue with the Department of Space. So I will say a few words about my experience since leaving the Department of Space. I mean, leaving the University of Kerala and joined the Department of Space in 1990. I will show those experiences also. I have had some wonderful experiences over the last 20, 30 years. Very talented people came up there also in the center where I joined as the director in 1990. So I can share a few words about that experience as well as my overall experience. I joined directly as a professor. I spent a long time in the United States, and it was a wonderful opportunity that I got in University of Kerala. Such a thing, it's not happening these days. It's a bit unfortunate, except the top universities, IITs, and they do invite, but the state universities haven't developed that culture of identifying the talent abroad and here in the country, and invite them to join in the faculty so that it can build up the strength of the department. It's not just the Kerala universities, all state universities are like that. So anyway, that's different topic altogether. But it's once again nice to talk to you all. So I hope I will get another opportunity to speak on 15th. I would like to share a few of those things at that time. Thank you. Oh, tell me. Tell me which batch you were. 18. 18. Ah. Oh. 89 I was there. I was there actually. And I think I left in 1990 November. So one more person I remember, I think around that time you joined, and he was one of the top atmospheric scientists today. Satish batch, were you? SK Satish? Oh, before. Okay. Satish joined, I think.
Satish sir, he was here only for MSc. Later, sir, he did a PhD in ISRO, SPL.
Yeah, I think quite a few of them who were our MSc students. After completing MSc, they joined Space Physics Laboratory from Saurabai Space Center. The present director, Radhika Ramchandran, was a Space Physics student here. And then Prabha Nair was a Space Physics student. Rajiv, who is now a G-level scientist, probably will be the next director there. He's a Space Physics student.
He used to come to department, sir. Rajiv used to come to department. Rajiv used to come to department.
Oh, okay. Oh, I see. All right. Yeah, I would like some of them to keep close contact. I don't know. I mean, they will be under their own pressure and all that. And I have initiated some work. In fact, one of the physics, I mean, the earliest students, Vikram was is a damn good student. I think he did his PhD with me, went into computers, and he's an entrepreneur there only in Trivandrum, IT companies. He started his own company. He and his son also an IT person. But Vikram is a space physics PhD under my guidance way back. And the space physics laboratory wants and defense wants. After working for some years in defense, he left and went to HP and then started his own. So like that, there were so many success stories. I can relate a few of them I remember, but many of them. I think quite a large number have made very successful careers and served this country in a wonderful way. Like, thanks a lot once again for giving me this opportunity to interact with you people, although informally. But I would like to construct a formal, a logical, sequential kind of story about my experiences in the Kerala University, maybe on 15th. Thank you very much.
Thanks.
I didn't get your name. I think I You told actually you 89 is oh, Georgie.
Hubert Joe.
Oh, okay. Yeah, okay. When did you join? 89. Last March. Oh, you joined. Okay. Very good. Welcome on board. Actually. Very good. All the best there. Yeah, build it up. Right. Thank you.